Okay, so today we're gonna discuss the compressive spring, which is subject to the fatigue loading. So for the previous courses, we were focusing on the static loading, right? Applied to the compressive spring. Okay, so for the following course, I'm gonna introduce how this compressive spring, which is subject to the cyclic loading, how to evaluate its endurance limits and the safety factor. Okay, and safety factor. Okay, so the fatigue loading of the helical compression springs. We already know the for this minimum tensile stress, right, of the springs can be evaluated by two parameters. First is the A and the exponent M, and both of them are materials dependent. Okay, so these two parameters are materials dependent. Okay, so we can look up the A and M coefficient, right, by checking any handbook. Okay, and now if we would like to discuss the fatigue loading, we have to take the endurance limits into account, right? And for the springs, we have to take the torsional endurance limits into account, right? SSE. Okay, SSE. Okay, so we have to consider the endurance limit, torsional endurance limit, okay, and whether the springs is surface modification, pinned or unpinned. Okay, pin and unpinned. Okay. Okay, so there's some parameters we have to consider first. Okay, so the SUT, okay, by checking the A and M coefficient, right? So when we get the SUT value and we can evaluate it's called the torsional yielding stress, right? Also, we can evaluate by checking the handbook. Okay, and then we have to uh, look at what is the torsional induced limits, SSE. Okay, so it would depends on the material's property and whether it is pinned or unpinned. Okay, so that's a recap what we already learned for this fatigue criteria, the fatigue, the SN diagram. Okay, so if you guys still remember the SN diagram for the completely reserved stress, remember that the SN diagram is only valid for completely reversed stresses. Okay, okay. So what is the completely reversed stresses? That's mean the mean value, the mean stress sigma n equals to 0, right? So the sigma n here equals to 0. Okay, so if this sigma n does not equals to 0, like this case, sigma m is right here, sigma m is not equals to 0, it is not completely reverse cycle, right? So in this case, we cannot use the SN diagram to evaluate, this fatigue loading of the spring. Okay, so in this case, it's valid by using the SN diagram. Okay. Okay. Okay, so we can, if this spring is under the completely reverse cyclic loading, so we can use the SN diagram. So we can figure out what is the stress applied to the springs, which is corresponding to the Nibov cycle, right? Nibov cycle by experiment. Okay, by experiment. And also we can figure out what is its SSE. Okay, what is SSE? The endurance limit, torsional endurance limit. Okay, torsional endurance limit. Okay. Okay, so spring fatigue, cyclic or dynamic loading. Okay, for the engineer Zimmerly, it provided data. Okay, so he worked on some experiment based on the wire diameter is about 10 millimeter. Okay, 10 millimeter. And this data is dependent on the size, materials, and the SUT, tensile stress. Okay, and tensile stress. Okay, so for example, this springs is a valve, a closed valve, or it's a valve for open and close. Okay, like your engine or like the some music instrument like trumpet. Okay, like trumpet. So I didn't have this. Maybe I have the picture later. So any valve which needs to close and open, right? So we can install a helical spring. Okay, we can install a helical spring. And in this case, there is an initial force applied to it, right? So you can think of these the brass instrument like the trumpet. Uh, when this button is not be pressed, the springs has a tension to close the valve, right? It's to close the valve. Okay. So when we apply a force, when we apply the force, this helical spring is being pressed, right? It's been pressed. Okay. And for this valve closed, the spring is with initial force, right? So in this case, it's loading situation does not equals to this called the completely reverse loading. Okay, so in this case, it should be uh belonging to this non-complete reversible stress. Okay, so it's sigma n, right? Does not equal to zero. Okay, does not equal to zero. Okay, there's one example here. So if this springs is under two stresses, cyclic loading, okay, 20 KSI and 90 KSI, right? So it's a cyclic loading between these two stresses, shear stresses, okay? So whose mean stress equals to 55, right? Sigma m, right? And sigma a, which represents the alternating shear stress, right? Alternating shear stress equals to 35 KSI, right? Equal to 35 KSI. So when this cyclic number equals to 10 to the power of 6 with this stress springs with the diameter less than 10 millimeter, we're fine. We're fine. Okay. An endurance strength component mean SSN, right? SSN here. I'm sorry. Here. SSN. Or say the tau m equals to 90 plus 20 divided by 2, right? And the alternating stress, SSA equals to 35 KSI, or tau A equals to 90 minus 20 divided by 2. Okay. So what's the most important parameters, or what's the most important values that we need? The sigma m and sigma a, right? For those what we already learned, those cyclic loading or fatigue criteria, right? Okay. Okay, so the endurance stress components we already know here, right? On the limit, but still safe. Okay, but still safe. Okay, so if we use the failure criteria, say the Goodman criteria, if you guys still remember that, right? It's a linear function. Okay, it's a linear function. So for this fatigue criteria that we already learned last semester, so we just use the sigma A, sorry, or SA or the SN, right? But now it's the shear stress for this springs is subjected to the shear stress. So we just modify it to tau A or SA, it's fine, or the tau M. Okay, so what's the Grumman criteria? Right, so it's what this equation was what we learned, right? Last semester. But now we have to consider the shear stress, right? So we just simply replace the sigma A to SSA to replace the sigma M to SSM, and so on. Okay, and so on. Okay, so we can just rearrange this equation. Okay, we can rearrange this equation. Okay, sorry. It should be, we can rearrange this equation. Okay. Okay, so finally we get, it's called the shearing endurance limit, or say the torsional endurance limit. It's the same thing, okay? The torsional endurance limit, SSE. Okay, SSE. Okay, and the SSU here, the ultimate shear stress, which also can be regarded as the torsional modulus of the rupture, which can be evaluated, by the relation that SSU equals to the 67% of the SUT. Okay, SUT can be looked up by checking the A and the M, right? Coefficients. Okay, so in this case, we can figure out what is the endurance limit is, right? And SSU, right? So we can point out 2 points, SSE and SSU, right? And this line is defined as the Grumman criteria. This line, okay, defines the Grumman criteria. Okay, and through the crashes that describe, right, the SSA 35 and the SSM 55. So we can just look at the point. So it's roughly on the limit here, right? It's right line on this straight line. That's why we say it's on the limit, but still safe if we use the Grumman criteria. Okay? Okay, so some examples here. For example, we can use the Gerber. Okay? We use the Gerber. Commonly used for springs. Okay? Okay? So this is what we learned for this fatigue criteria, right? And the same will just replace the sigma A to SSA, sigma M to SSM to SE to SSE, SUT, just replace it by the SSU. Okay, so in the same case, the SSE equals to 35 KSI, SSM equals to 55, SSU equals to 0.67 SUT, right? And we can replace the SUT here, so we can check the A and the M coefficient, right? Okay, and we just rearrange this equation, right? We can get this Gerber's SSE, the Gerber's shear induced limit. Okay. So we can think of the SA versus the SSE and the sigma N versus the SSU. Okay, SSU. So we can just replace replace the this, right? SSA replaced by the tau A, okay, and SSM can be replaced by the tau M. Okay, so if you already know this different fatigue criteria, so you will in your mind you are clearly realize which number or which values can be used. No matter the symbol is not quite important. Sigma A or tau A or the SSA, tau M or SSM. Well, it's similar. It's the same thing. Okay, so if you already fully understand what is criteria that can be utilized, those symbols, well, it's not the problem. Okay, so so the tau A, the alternating shear stress equals to there's a KB parameters times, right, this term. Okay, and the FA, the alternating force applied to the springs, equals to the difference between the maximum and minimum force divided by 2. And the mean shear stress equals to KB, the parameters, right, with this term. And the difference is that the force for the tau A is the FA, and the applied force for the tau N is Fm. And Fm equals to the maximum minimum summation of the max and the minimum force divided by 2. Okay, divided by 2. Okay. So for this material surface treatment, if there's springs with pin and unpin. Okay, so just use the beads to bombard the surface of the springs, and the surface will has the tension after pin. Okay, and this permanent indentation by pinning will induce the residual stress on the surface. Okay, so for the spring with the pinning, there are two type of residual stress on its surface. First is the bending tension, right? When we just wound this spring wire, there's a tension, right, on the surface, outer fiber. And if this spring wire is pinned, that's mean we use the beads to shut its surface to generate the permanent indentation, and this indentation will induce the residual stress, which is compressive. Okay, so for this surface stresses, which is combined with the tension and the residual stress, okay, residual stress. That's mean this springs as the strengthened surface, okay, strengthened surface. Okay. Okay, so for this pin springs with the same cyclic loading, 20 to 135 KSI. Okay, so we can just calculate its the mean stress, okay, and alternating stress. Okay, mean stress and alternating stress. If we use the Gerber's criteria, the SSE, right, equals to this equation, we just plug these two numbers, right, here and here. Okay. Here and here, okay. So for the exemplifying that the size, materials, and tensile strength has no effect on the endurance limits of the spring steels in the size under 10 millimeter, and the testing found the endurance strength components for the infinite life on pin springs, the SSA, okay, and the SSM, okay, the mean shear stress. And for the pin springs, whose SSA equal to 395, almost 400 megapar, and the SSM equal to 534 megapar. So this numbers tells us these springs as pinned we have this higher, the alternating shear stress and the main shear stress. Okay, these constant values are used for the Gerber or the Goodman failure criteria to find the endurance limits. Okay, if this stress is made by steel, okay, made by steel, and we can use this number, okay, to find the endurance limits. Okay. Okay, and for fatigue loading for the helical springs, compressive springs. So this is the examples that with the unpinned spring, whose SSU, and by using the Gerber, okay, for the share, we can get SSE, the shear induced limit. Okay. And by the Goodman, it will be that SSE equals to the 47.3 KSI. Okay, and each possible wire size will change the induced limit since SSU is a function of wire size, right? Because SSU is roughly equals to 67% of the SUT, right? SUT, right? And SUT depends on the parameters A and M, right? And wire diameter, okay? And wire diameter. Okay, and yes, we find that for the polish notch-free cylindrical specimen subjecting to torsional shear stress, the maximum alternating stresses that might be imposed as constant and independent of the mean stress. And many compression springs approach these conditions. And this failure criteria is known as the sign failure criteria. Okay. Okay, so the previous we already the previous courses, okay, we only fix it on the compressive spring. That means this force is compress, right? The first compress. But now, what is if the spring is under extension, right? What is the extension? So what's those parameters that we have to take into account, right? So those parameters such as the maximum tension stress and the maximum torsional stresses and the bending and torsion stress correlation vector. And what's the initial tension or initial torsion? Or what's the freelance body coil and active coil? Okay, so for this extension spring, this force is subjecting to extension, of course, right? Right. For the previous, the compression spring is under compression. Okay. So for this tensile stress, we have to take into account and the initial tension. What's the initial tension already applied to this spring? Okay, and those equations can still apply for the extension spring. Okay, so this like this maximum shear stress equals to KB, right? This parameters times this term, and also the bending stress. Okay, and the bending stress. Okay, bending stress. Okay, so we have the point sigma A here. Okay, so suppose this is the extension spring, right? And in this case, the spring is contact tightly, okay, tightly, and there's a curvature R2 here, okay, and there's a maximum stress concentration when an extension force applied to it. Where? Here. Here. Okay, so this is the cross section of the wire. And at this point in the fiber of this hook has the maximum stress concentration. Let's say this is the point A right here. Okay, right here. So we can analyze these stresses, right? Right? So for this stress, the bending stress, or for the stress, bending stress applied to point A equals to the my over I, right? The bending stress. Okay. And also there's the normal stress, right? And this surface. And this surface. Okay, you got it? Right? And this bending stress from this moment equals to F times D over 2. This is the mean diameter, the mean core diameter. Okay? And A is the cross section of the wire. Right? So you can think of, we have this distance, right? Half of D here. And when we move this force from this position to here, right? That means there's a moment, right? Therefore, at point A, there are two stresses applying. One is the bending stress and the normal stress. And we can just simply calculate the sigma A, right? Equals to this term. Okay. And the sigma A, right? We already got equals to this term. Okay. And we can extract the force outside. Okay. The bracket. Okay. Okay, move the force and the force outside the brackets. And we can just reorganize this term. Okay, reorganize this term. Okay, and we provide the correlation vector Ka here. Okay, we need put correlation vector. It's called the bending stress correlation vector Ka here. So this Ka is related to the curvature, or say the radius. Okay, so the Ka is a function of the C1. Okay, and C1 equals to the 2R1 over the wire diameter. Okay, so previously we already mentioned this, the R1, right? Sorry, R2, and R1, right, is the radius of this hook. Okay, we say the C1 is the geometric vector. Okay, similarly, Ka is the geometric correlation vector, and C1 is not. Okay, so C1 which is not equal to the spring index. Okay, the spring index. Okay, so this is a sigma A. And now let's look into the tau. That's mean the shear stress. Okay, tau B, which doesn't mean that the point B. We just give a name, tau B equals to a correlation vectors times this term. Okay, and this equation, the KB does not equals to the KB that we mentioned previously. Okay, it's not equal because this KB is also defined as a geometric vector C2, and C2 will equals to 2R1 divided by wire diameter. Okay, wire diameter. Okay, so when this R2 approach to 0, that's mean the C2 approach to 0. Right? C2, that's mean this corner is almost no. R2 approach to 0, that's mean C2 approach to 0. Right? So what's the situation if the C2 equals to 0, 0, 0, right? That's mean we'll get the higher shear stress, right? We'll get the higher shear stress at this point here. Okay. Okay, so for this extension spring, this is a closed wood spring, right? So that's mean the edge, uh, the pitch is approach to 0. Okay. So if this let's think of for this extension spring, okay, which is different from the compression spring, okay, right? Because the pitch, right, as because the each coil is contact tightly, okay, tightly. Okay, and we need the force if there's non-zero force. Initially, there's a non-zero force to extend it, to extend the spring. Okay. And for this fabrication of this extension spring, we need each coil is contact tightly, right? So we have to apply residual stress by torsion. That means during this fabrication, we have to twist this wire. Okay, twist this wire. Okay, twist the wire and rotate the mandrel. And rotate mandrel. And this twisting will create Fi. Also, for this mandrel rotating, we have the bending, right? As I mentioned previously, as a bending. So the initial tension applied to the spring, even without any zero force. I would say the external force. Okay. And what is the Fi is? What is the Fi is? And what is the shear stress is with this initial tension. Okay. So for this case that without the Fi, the initial tension, if the spring follows the Hooke's law, F equals to Ky, right? Is what we learned previously. And for this springs with the initial tension, the initial force, we have the jump to here, to specific point. Okay, and this force, it will equals to the Fi, the initial tension plus Ky. And this Fi comes from the fabrication, the twisting and the mandrel rotating. Okay. Okay. Okay, so similarly, we have to find the spring constant or spring rate first, right? Depends on its material's property and dimension and the number of active coil. Okay. The G, the dimension, and number of active coil. Okay. And there's a relation between the active coil and the body coil. Okay. If we, if this material is isotropic, okay. So this number of coil will equal to the number of the body coil plus the shear rigidity divided by the Young's modulus. Okay. Okay, so the active number of coil and the number of active coil and the number of the body coil. That's this relation. Okay, so let's define the geometry, the dimension of this extension spring. Okay, so for the free length, it's from the hook, the end of this the inner ring, right? The distance between this end of this two end of this inner ring. Okay, we call this free length. Okay, L naught. Okay, so let's calculate the first coil to the end. We define it as the length of the body length. Okay, the body length. Okay, and the length of the body equals the number of the body coil plus one, right? Okay, so we have to count the number of the body coil, right? Plus one wire diameter. Okay. Okay. And the free length L naught equals to the L naught equals to this term is what? It's the length of the body, right? Here. Plus 2 times the main coil diameter minus the wire diameter, right? Plus this distance and this distance. Okay, so finally we can get L naught for the extension spring equal to D times 2C minus 1 plus MB. Okay, and C here is the spring index. Okay, it's the spring index. Well, we can manipulate this equation to convert it in terms of the spring index. Okay. Okay, so for initial tension, how to evaluate initial tension SSY equals to the specific percentage of SUT, right? SSY represents the shear unit stress. SY is the tension unit stress for extension spring. Okay, both of these two are related to the SUT. And SUT is depends on the A and M, right? Coefficients. Okay, and allowable shear a specific percent of the SUT. Okay, and this T allowance represents the torsion unit shear stress for extension spring. So we have the shear unit stress, I have the tension unit stress, I have the torsional unit stress. And no matter which one, it can be evaluated by SUT. Okay, and here the Fi is required to start stretching the spring. Okay, stretch the spring. When removing the spring from this mandrel, okay, the Fi is applied. Okay. Then check if it lands within this range. Okay. So we define by experiment, we define the stress, initial shear stress due to this Fi, okay, with the English units, okay, the English units, okay, and this tau I can be evaluated by the Fi first, okay, Fi, the initial force without KB first, okay, we just simply evaluate, okay, simply evaluate. Okay, and in SI units, we can use this equation to evaluate its tau I, the initial stress. Okay, initial stress. Okay. Okay, we can evaluate the sigma I by using this equation first without the KB. Okay, okay. Let's first evaluate whether this sigma I is beyond those like the let's say we can first evaluate the tau I, right? Right? Whether it's within the range of this. If this tau I is beyond those values, we say, okay, so it's maybe causes failure, right? Right? So we can use this equation to evaluate first, and then we can see whether this value is within this range or not. Okay, this range or not. Okay, so there's let me see. Okay, so let's look into this example first. Okay, so suppose we have a springs with the spring wire diameter is 0.042 hydro steel and outer diameter is 0.265 inch. And R1 is 0.1 inch, R2 equals to 0.08 inch. The maximum force applied is 6 pounds. The initial tension is 1.5 pounds. And the number of the body cost 12.5. And what is the safety vector is? And what is the length when extended? Okay, so the length equals to the L naught, the free length, plus the maximum deflection in y direction, right? And the L naught we already know from this previous slide, right? And we can calculate its spring index, and we know it's the MB. So the L naught, the free length, equals to 0.95 inch. Okay, 0.95 inch. Okay, and the Y max equals to the force divided by spring constant, right? And the force equals to the F max, the maximum force minus the initial force divided by K. Okay, and the K is dependent on the material's property and the dimension, right? So we can just figure out what is the K parameter is and plug this K here. So the Y max, the maximum deflection, equals to 0.1427 inch. Okay, and this K is the slope of this FY diagram. Okay, and the number of the active coil equals MB plus the shear rigidity divided by Young's modulus. These two are materials property. So we can find the number of active coil is 12.9. Okay, and the factor of safety. NA, you have different cases. Okay, let's look into the NA. The safety vector equals to the SY, this tension yielding stress divided by sigma A. Okay, remember the hook, right? The hook right here, the point A. Okay. Okay, so the SY, the tension yielding stress, will equal to the specific percent of the SUT and sigma A. That's what I mentioned previously. If we extract the force out, we can times this term. Okay, times this term. Okay, the second we have to take into account the shear. First is the tension, right? And the shear. And B, that is the T allowable, the allowable shear stress divided by the tau B, and the T allowable will equal to specific percentage of the SUT. Okay? And the sigma B equals to the KB times this term. Okay? And finally, we use the SSY to evaluate the safety vector. SSY divided by the maximum shear stress. Okay, and SSY equals to 55% of the SUT. Okay. Okay, because this questions just mention the material's property, but without any surface treatment. So we can define as the 45% torsion. Okay. So we get the SSY equals to 150.2 KSI. Okay, and the maximum shear, okay, equals to this term. Okay. It's the same as this one. And SUT is the first value that we have to figure out. And we can check the table to find the A and M. Okay, and A equals to 140, the M equals to 0.19, and the Y diameter is the 0.045, right? Therefore, we know what the SSUT is, 255, and we can plug this number here to figure out to estimate what the SSY is. Okay. Okay, and also we can just calculate the allowable shear stress. Okay, allowable shear stress, the 0.5 times SUT. Okay, it's about the 102.3 KSI. We say the shear that we have to take into account is at the end of this hook. Okay, the end of this hook. Okay, the end of this hook. That's what I mentioned previously. The most critical part I have to take into account is the one is right here, right? A, and the here, right? So for the first safety factor, we consider the tension and the normal force, the bending and the normal force, right? At this cross section. And for the NB, that's mean you have to think where is the maximum shear stresses applied? What is it here? Okay, the here. Okay. Okay, so the NB means we have to consider where's the maximum stresses applied. Okay, and this N represent that we have to consider the torsion within the springs. So we have at point A and at the point, we cannot say point B, but we say the location where the maximum shear stress applied. And also have to consider the torsional shear stress for this whole extension spring. Okay. And no matter what, we have to figure out what is the SUT is first. Okay. Okay, so the S and A, that's mean for this sigma SY divided by sigma A, we consider the normal stresses. This NA is about 1.7. Okay, 1.7. Okay, 1.7. Because the SY equals to 75 points here. 75% of SUT, and SUT we already find is 255. And the sigma A, right? You can calculate the parameter, the coefficient Ka right here by calculating the C1. So we can plug this number right here. This number here to find this safety vector. Right? The safety vector at point A, which is under the tension. Okay, under tension. Okay, so for this maximum shear location MB, similarly, we find the T allowable stress and the TB, Okay, so we have to calculate the coefficient KB by the geometry, right? So we got this tau B equals to the 58.3, and the T-Alombo stresses is 102, right? So we plug this number here and here, and we get safety vector equal to 1.75. Okay. Okay, and finally, we have to consider the torsional stress, right? And the torsional stress and the maximum shear. And the maximum shear. Okay, and we plug these numbers here and here, and we got 1.966. Okay. So we already know, right? What's it? We already know the condition. So what is the safety vector is? What's the safety vector is? Well, it depends on how you select it. Okay, so we can by using uh the safety vector at the point 8. Okay, safety vector at the point 8. Safety vector at point 8. The bending at the hook. The bending at the hook. Okay, and the length when extended are equals to the initial length plus the Y max is 1.073. Right? So we got this. We should select the smallest safety vector. Okay, smallest safety vector. Okay. Okay, so the next course will be ended here, and next we are gonna introduce the this torsional spring. Okay, this torsional spring.